Welcome back. We're trying to figure out what the difference is between our actual mystery value and the Taylor polynomial approximation of our value. And spoiler alert, we're generally not going to actually find the exact value of that error. If we knew what the exact value of the error was, then an approximation wouldn't be necessary because we could just take our approximation and our error and combine them together and get the exact value. No more approximations. So instead, we're going to be looking at something that gives us a worst case scenario. We're going to say, how close can we possibly get and be sure about it? Okay, so that's where that z comes into play. So we say that z is some value between x and c. Okay, and when we say that, we can say that using two different intervals, right? We could either say that it's going from the interval x to c, or is going from the interval c to x. Why do we have to write them both? Because intervals are always written small to big. Small comma big is always our interval notation. So depending on whether x is the smaller one or c is the smaller one. I would say most of the time c is larger than x, because a lot of times, I would say that x is larger than c, because a lot of times c is equal to 0, and a lot of times x is some positive value, but there's no requirement there. All right, so what we're trying to do now is not find what z is, but say, picking values between c and x, how big can we make that n plus first derivative? Okay, now a lot of times it's a very hard question to answer, and that's what makes these problems so hard. But there are certain patterns that we're going to find in some of these questions, and we'll kind of figure out how to deal with them. So example 1, if we read the instructions here, the given information, they're really kind of handing this to us on a silver platter. Let f be a function with 5 derivatives on the interval 2 to 3. And here's the key right here, guys. We're given, or we can assume at least, that that fifth derivative of the function is less than 0.2 for every single x value between 2 and 3. That's a really convenient thing to know because, again, that's this part right here. Okay? So we don't know what the fifth derivative is. We don't know what the function itself is. We don't know what the fifth derivative is, but we do know that that fifth derivative, that numerator of the Lagrange error, is guaranteed less than 0.2. Okay, so that's really, really golden information for us because that's the hardest part to figure out. They've just given it to us. Okay, and notice that they're talking about the fifth derivative is less than 0.2, and they're talking about a fourth degree Taylor polynomial. How perfect is that? So from here, we should be able to figure out a lot of the stuff that's going to go into this equation right here, right? So for example, since we're dealing with a fourth degree Taylor polynomial, then we know that n right here, n equals 4, which is kind of nice because that means that n plus 1 equals 5, right? So if n equals 4, then n plus 1 equals 5. So this is exactly the information we need to deal with this. Okay, so c equals 2. That's going to be the center of our Taylor polynomial, and we're going to try to approximate f of 3. Okay, we have no idea how to find f of 3. All they're asking us right now, actually, is to figure out how accurate the approximation is. All right? So let's see. How accurate is it? Well, it's as accurate as the worst case scenario of our error. So our error of our fourth degree Taylor polynomial, evaluated at x equals 3, right, is going to be equal to, well, according to our formula up there, we've got the fifth derivative of f evaluated at some mystery value z divided by the n plus 1 factorial is 5 factorial times, let's see, x again is 3 and c was given to be 2 and then n plus 1 is 5, so we put that in there. Notice that that's 100% equal. I used a straight lined equal sign there because that is the theorem, right? We know that there is some z value that will make that equation true. We don't know what that z value is, but we do know that the z value is between x and c. Oh, x and c are 2 and 3. Oh, wait a second. We have this information that tells us that the fifth derivative between 2 and 3 is always less than 0.2. Oh my goodness, that's so perfect. So we don't know what the error is, but we do know that the error guaranteed 100% is absolutely positively less than if we replace this thing right here with 0.2. We know that 0.2 is too big, right? So 0.2 goes on top, and 5 factorial goes on bottom. And then 3 minus 2 is 1, so 1 to the fifth. And you just punch that into the calculator. And that's going to, it says round to 3 decimal places, so when you punch that into the calculator, you get 0.001667. So I'm going to go ahead and round that to 2. Okay, so remember, the error, the r sub 4 of 3, is telling us the worst case scenario, the biggest error possible according to the Lagrange error bound. The biggest difference we could possibly make between the actual value of f of 3 and the approximate value that our Taylor polynomial gave us. Okay. Before I move on, I want to try to use this. I want to maybe do like a second A question. I want to try to change this and say, what about if we wanted to estimate the error if we were approximating f of 2.5? Okay. Now think about 3 versus 2.5. Should the x value of 3 give us a better approximation or an x value of 2.5? Now, if you remember how these things work, remember that Taylor polynomials approximate a function very well close to the center of convergence, right? That c value. So since 2.5 is closer to c, then that means that we expect that f of 2.5 is going to be closer to its Taylor polynomial approximation than f of 3 is to its Taylor polynomial approximation. So that means that our errors should be smaller. So let's see what happens. If I do r sub 4, not of 3 anymore, these errors don't just depend on how many terms we go out to, but it also is determined by how close we are to that center, in this case the center of 2. So when we do r sub 4 of 2.5, almost the same stuff, except we're going to see that this is, well, most of it's exactly the same, right? We still have the fifth derivative evaluated at some mystery value z, and then it's still 5 factorial. Well, this time it's not 3 minus 2.5, it's 2.5 minus 2. I'm sorry, it's not 3 minus 2, it's 2.5 minus 2. But that's still being raised to the fifth power, okay? And if you'll notice, we actually still know, since this interval goes from 2 to 3, 2.5 is within that interval 2 to 3, so we can still replace this the exact same way with a 0.2. The only difference is we've got not 1 to the fifth power, but 0.5 to the fifth power. And how does that change our answer? Well, if we decide to round to the nearest 3 decimal places, then you're not going to get much of an interesting answer because you're going to get 0. But if we go a little bit farther, we're going to get 0.000052. So our error is much smaller by 2 orders of magnitude or so when we get closer to that that center of x equals 2. Of course, if we try to evaluate f of 2 versus p sub 4 of 2, then we would get the exact same answer because everything matches at the center. But when we're getting very close to the center, those errors are going to be very, very close to 0. All right. Anyway, back to the degree 4 polynomial approximation of the function at x equals 3. We're given some more information now. Okay. So again, this is the Taylor polynomial evaluated at 3. They didn't tell us what the Taylor polynomial was. We don't need that. All we need to know is what we get when they plug in 3 into that Taylor polynomial. And they tell us we get 1.763. Again, this is not f of 3. This is an approximation of f of 3. So we know that the Taylor polynomial approximation P4 of 3 is approximately equal to f of 3. They're close. That's the whole point of the Taylor polynomial. We're using it to approximate that unknown function f. Okay. So what do we do with that error? Well, that error tells us that the difference between those two has to be between, or it has to be no greater than 0.002, right? That's what we found up here. So basically what we're going to do is we're going to say, well, that P sub 4 of 3 plus R sub 4 of 3 is our maximum possible value of f of 3. And we can do the same thing on the other side and say P sub 4 of 3 minus the error, the maximum possible error. That's going to give us the lower bound, okay? And we know that that in the middle we've got f of 3 is somewhere in the middle, right? F of 3, let's make that a little more legible. F of 3 is somewhere in the middle, so it's definitely smaller than or possibly equal to that, and it's definitely smaller, greater than or possibly equal to that. So what is P sub 4 of 3 minus R sub 4 of 3? Well, that's 1.763 plus, or I'm sorry, minus 0.002. So that's 1.76. Let's see, 3 minus 2, I think that's 1. All right, so that's the lower bound for f of 3. And then when we add 0.002 to this number, we get 1.765. So f of 3 is guaranteed to reside between these two values. Okay? Doesn't want to let me box that in. Let me scroll up. Maybe I can box it in here. Okay? So now it asks the question, could f of 3 equal 1.778? Well, 1.778 is greater than the largest possible value of f of 3. So no. Could it equal 1.764? Well, 1.764 is between 1.765 and 1.761. So sure, it could. Yes, it's possible that f of 3 equals that because it resides within the interval.